take a look at practice question set number 22. A couple of really good questions on this, especially the last one. This one says several transparent substances are arranged in layers so that the surfaces are parallel. Light rays directed at the substances as shown below. Now, of course, we know that each of these substances has a slightly different index of refraction depending upon what frequency of EMR that we use. But we're saying in this question that for this frequency, whatever it is, the index of refraction is whatever it is that's listed. Air is 1.0, water is 1.33, and so on. We know that this one is on our data sheet, and I've told you before that if you need the other indices of refraction, they're going to be given to you somewhere, either buried in a page of information or given to you in a diagram like this. They're going to be somewhere. All right, we want to find, what do we want to find on this? Question number 1 says, light travels slowest through which medium? How are we supposed to figure that out? Where does light travel slowest? Yep. Yeah, as n goes up, v goes down. So we're looking for the slowest speed. We're looking for the highest index of refraction. That means it's going to be glass, 1.50. The answer is C. Numeric response number 1 says the angle of refraction in the glass is what? Now, this is kind of an interesting one here. Hey, this is kind of an interesting one. Let's label some angles here, and then I'm going to poll you to see how many people did it one way, and then how many people did it the other way that is a fair bit shorter and quicker. We're going to call this one, okay, I don't like those letters there so much. I'm going to call this one angle 1, angle 2, angle 3, angle 4. We want to find the index of refraction in the glass, so that's far enough, right? Because I want to find theta 4 here, right? Does that make sense? Yeah, I want to find theta 4. Well, because these lines are parallel to each other, theta 2 is the same as theta 3, agree? And theta 4, well, theta 4 is the same as theta 5, although it doesn't really matter about that, right? The important thing is theta 2 is the same as theta 3, agree? So what I could do here is say sine theta 1 over sine theta 2 equals n2 over n1, get theta 2, and then say sine theta 3 over sine theta 4 equals n4 over n3, solve for n4, knowing that theta 2 is the same value as theta 3. Does that make sense? How many people did it that way? Good. That is absolutely correct. But there is a shortcut. Does anybody spot the shortcut? If this ratio like of n2 to n1 is the same as theta 1 over theta 2, and then this ratio is the same as this ratio, then isn't sine theta 1 over sine theta 4 the same as n4 over n1? Absolutely it is. Now, that only works if these lines are parallel to each other, because it only works if theta 2 is the same as theta 3 here. Does that make sense? Like if these lines are not parallel to each other, the boundaries are not parallel, that wouldn't work. But because they are, sine theta 1 over sine theta 4 is equal to n4 over n1. Does that make sense, guys? Like this to this is the same as this to this. Well, remember that sine theta 2 and n2 are the same as sine theta 3 and n3. So we can just say sine theta 1 over sine theta 4 is equal to n4 over n1, and it works just fine. When we solve for theta 4 here, what do we end up getting here? Sine 36.8 degrees over sine theta 4 equals 1.50 over 1.00. This goes up by multiplying. The 1.5 goes down by dividing. And then we take the inverse sign. We do that. I end up getting 23.5 degrees. 23.5 degrees? Yep. Is that right?
Yeah.
Do you have a question? Or you...
No, I thought you were going to say who got that. So
okay.
Just jump the gun.
All right. Who got that? Good. The one benefit to doing it the way that I did it, well, the two benefits, right? It's quicker, right? But you know that on a test, you basically have the time that you need on a test. And on a diploma exam, you certainly have the time that you need with 6 hours, right? time's not a factor for you, but sometimes we can do something a little bit quicker, then we're finished the exam a little bit sooner and our mind is a little bit fresher. We're not quite as tired by the time we get to the end of the exam. The other benefit to it is that it's one calculation instead of two, which of course reduces our chances of making a mistake, especially a rounding error, because if you did it the longer way, you'd need to use the answer from one to go into the next one, and if you rounded wrong, then you might end up getting 23.4 or 23.6, which of course is going to be marked wrong. But if you do everything properly, either way should absolutely work. Now, this is not expressed in scientific notation, so we're going to express this just as 23.5, including the decimal place. All right, let's take a look at question number 2. The critical angle when light passes from water to air. We didn't really need to be told that it was passing from water to air. We could have just said the critical angle between water and air is, and we know that it's going from water to air because we know that for total internal reflection to take place, it must be going from high to low index of refraction. Remember that? If you're going from low to high, then the light's going to slow down, and if the light's going to slow down, it can never reflect. It's got to speed up, therefore it's got to be going high to low index of refraction. Let's say sine theta c over what? Over sine 90, which is just 1. So let's just call it sine theta c is equal to n2 over n1. So sine theta c is equal to 1.00 over 1.33. Pretty sure I got that right, but if I mixed it up, the order of it, what's going to happen? Error on the calculator. Theta c is equal to the inverse sine of that, and when we do that, we get 48.8 degrees. And once again, no scientific notation here, we just express it as 48.8 degrees. Oh, now, this last question. This is a good one. This is a tough question. I don't remember the statistics on this when this appeared on an diploma exam, but I would hazard a guess that they were not good. Okay, this is a tough question. I think all 4 parts of it are challenging, but I think there's a couple parts that are particularly challenging. We are given some information here about a group of students performing an experiment. It says, we want to test the effect of wavelength on the index of refraction of an acrylic rectangular prism. The following ray diagram is produced when a red laser beam was incident on the prism. So here we go. The red laser beam is going this way. Okay, it hits the boundary between the air and the acrylic. You can see that you got theta 1 measured, theta 2 measured from a normal line, and then of course it goes from the acrylic to the air at the other side, although that's not labeled. Let's label it. Okay, let's finish drawing this diagram, okay, when it leaves the acrylic air boundary. Now, I don't know what the index of refraction of acrylic is, okay, but I know that as it goes from air, which has an index of refraction of 1, let's say acrylic is 1.4, let's say. Let's make it up, 1.4. As it goes from 1 to 1.4, the light slows down, theta decreases, and then as it goes from 1.4 back to 1, the light speeds up and theta increases. What do you think this angle is going to be compared to this angle out here? It's the same, right? Think about that. It's the same. If light slows down a certain amount when it goes through this boundary, then it's going to speed up by the same amount when it goes in reverse. That make sense? So I'm going to draw this. Try to draw it, that is, so that, is that okay? It's hard to see it from where I am, from this being this close, but this line and this line should be parallel to each other. If I call that theta 1, I'll call this theta 4. We know that theta 1 is going to be equal to theta 4. Does that make sense? If it slows down by a certain amount, it speeds up by the same amount. If the angle changes, decreases by a certain value, then it's going to increase by the same value when it goes in reverse from acrylic to air. Now, let's see what else we got here. It says the second trial is conducted using green laser light. The angle of incidence at the air acrylic boundary is the same as in the first trial. Okay, so let's draw one with green light now. the same angle here, or at least as best as we can. What's going to happen to the green light as it goes into the acrylic prism? It's going to bend, right? It's going to speed up or slow down? Okay, remember, we're saying that we're making this up, 1.4. We don't know exactly what it is, but okay, it's just to illustrate to us that it's going to, as n goes up, v goes down. Theta goes down as well, right? How is the angle theta 2 for the green going to compare to the angle theta 2 for the acrylic? Yeah, let's go to our 137th favorite band of all time poster over here, Pink Floyd, Dark Side of the Moon. This is dispersion, right? We know that dispersion happens because glass has a slightly different index of refraction for each different color. Okay, we remember which colors have the highest index of refraction by looking at this picture. Red produces the lowest index of refraction because it bends the least. Green or violet produces the highest index of refraction because it bends the most. Does it make sense? All right. So the highest index of refraction between red and green would exist for green. That means green would bend more. Green bends more than red. That means that it's going to bend more like this. You see that? See what I'm doing there? Now, careful. It bends more because it has a higher index of refraction, but theta 2 is going to be less than it is for red, right? It's bending more, which makes it for a smaller angle. Now, let's see what happens when it gets to the other side. What do you think is going to happen here? Well, if the boundary between the air and the acrylic caused the light to slow down by a certain value, when it gets to the acrylic air boundary, it's going to cause it to speed up by the same amount. The angles will change by the same amount as well. Therefore, we're going to end up having, are those parallel? Close. This one and this one should be parallel again. This is going to be labeled theta 1. This is going to be labeled theta 4. And once again, we're going to say theta 1 is equal to theta 4. Make sense? Okay, what are they asking me here? What are they asking me now? It says match the numbers of the comparisons above with the descriptions given below. The index of refraction of the prism for green light compared to the index of refraction of the prism for red light. Again, think of that picture over here. For green light bends more, therefore green light must have a, I shouldn't say green, I was going to say green light has a higher index of refraction. Light doesn't have an index of refraction. Acrylic has a higher index of refraction for green light, right? So we look down at our list here. Greater than, okay, we're going to say it's greater for green light than it is for red light. What about theta 2 green compared to theta 2 red? Theta 2 green compared to theta 2 red. Yeah? It's smaller, right. It's smaller. It bends more, but the angle is smaller. So we're going to say smaller is 1 less than. We're going to put that in as a 1. The speed of green light within the prism compared to the speed of light of red light within the prism. The index of refraction for green light is higher, so the speed is going to be smaller, right? So it's going to be a 1 as well. And the angle of refraction for green light compared to the angle of refraction for red light as they leave the prism. This was what I thought was the really tricky one, and that's why I kind of led you through what I did before we even really looked at the question here. How does the angle of refraction going into the air for green compare to the angle of refraction going into the air for red? It's the same. It's the same. Now, inside the acrylic, different things are happening, right? But if theta 1 is the same for green as it is for red, and theta 1 and theta 4 is the same for green as it is for red, if theta 1 is the same as theta 4, then theta 4 has to be the same for green as it is for red, right? Green slows down by more than red does. But then what happens when it reaches the acrylic air boundary? It speeds up by more. So it ends up going in the same direction when all is said and done. So the answer for that is 2, 1, 1, 3.